There is a profound elegance in how geometric shapes constrain one another within a bounded space. This problem beautifully captures that harmony by nesting two tangent circles inside a right-angled triangle ABC, where angular equals 90 degrees, side AB equals 12, and side AC equals 20. The challenge requires finding the radius of a smaller circle Q that is simultaneously tangent to sides AC and BC, as well as externally tangent to the triangle's main incircle, circle O. What makes this puzzle so captivating is the transition from the macroscopic scale of the triangle down to the microscopic, self-similar corner scaling, revealing a rhythmic algebraic relationship hidden within a simple right angle. Solving this puzzle requires a systematic, multi-layered approach that bridges classical Euclidean geometry with trigonometry. First, the length of the hypotenuse BC is established using the Pythagorean theorem, which directly allows the calculation of the larger incircle's radius via the area to semiperimeter ratio. From there, the problem shifts focus to vertex C. By drawing a line from vertex C through the centers of both circles, we exploit the properties of homothety and angle bisectors. Using half-angle trigonometric identities, we determine the exact scaling ratio between the two circles based on how sharply they are wedged into the corner of the triangle. By applying the Pythagorean theorem, the hypotenuse BC is found to be the square root of the sum of 12 squared and 20 squared, which simplifies exactly to 4 times the square root of 34. This yields a primary in radius for circle O equal to 16 minus 2 times the square root of 34. Next, analyzing vertex C gives the cosine of angle C as 5 divided by the square root of 34, which translates to a half-angle value where the sine of half of angle C equals the square root of the quantity 1 minus the cosine of angle C, all divided by 2. Substituting these precise components into the corner tangency scaling formula, where the radius of circle Q equals the radius of circle O times the fraction of 1 minus the sine of half of angle C, divided by 1 plus the sine of half of angle C, the nested layers of radicals resolve beautifully. The final exact radius of the smaller circle Q is 16 minus 2 times the square root of 34, multiplied by the fraction of the square root of 2 times the square root of 34, minus the square root of 34 minus 5. Divided by the square root of 2 times the square root of 34 plus the square root of 34 minus 5. This yields a crisp decimal approximation of approximately 2.510.